In this video, we're going to talk about alkanes and their specific reactions, including combustion and radical substitution. We're starting off with combustion, and we're going to talk about combustion in terms of it being an oxidation reaction, and in chemistry, you can talk about it in terms of adding oxygen or of losing electrons, and hopefully you remember oil rig. But for now, we're going to go into the lab where we can look at the different types of combustion reaction and how that physically works and looks like in the laboratory. Welcome to the lab, and we're going to talk through combustion. So we have two Bunsen burners set up. One on my right is complete combustion with the roaring blue flame, plenty of oxygen, and then we've got incomplete combustion with the orange safety flame, which has limited amount of oxygen. Let's look at this a little bit more closely. So if I go down to the collar, you can see the collar is completely open. Now that collar being completely open lets in lots of oxygen. If there's lots of oxygen, you will oxidize your hydrocarbon fully. Now in your hydrocarbon you have hydrogen and carbon. So the fully oxidized version of carbon is carbon dioxide, and the fully oxidized version of hydrogen is water in terms of combustion. So if we look here and we take our gas that we've got, which is propane, and you can use any one, and I would really say stop the video now, try and write out a few equations with different hydrocarbons. But we've got propane adding to oxygen, loads of oxygen, so we completely combust our C and our H, and we get carbon dioxide and we get water. Now that all happens because of this collar's open, because letting in all of this oxygen, and it produces a lot of heat. Now when we talk about the heat, let's look at this flame. So you look at the flame and you can see there is a triangle, a blue triangle. Now that blue triangle, and I see students do this wrong all the time, it's constant, they never heat it in exactly the right place. Now the top of this triangle is the hottest part of the flame. So that blue triangle coming straight out of the Bunsen burner, the top of that blue part is your hottest part. So that's where you need to heat if you can. Now, we're now going to move on to incomplete combustion, and then we'll come back and compare the two. So incomplete combustion has the air hole, but it's closed. So it's limiting the amount of oxygen you can join up with the gas. Therefore, you can't completely oxidize the carbon and the hydrogen. So the two versions of carbon that are not completely oxidized are carbon itself, when it's not oxidized at all, and carbon monoxide. I'm going to talk about carbon first. So if I place this gauze, and I place this gauze over here, for a short period of time, it will start to produce lots of carbon there. You can see that's lots and lots of carbon there. But then if I take this and I place it over here, and I place it on the blue part of the flame, and you can hear the noise there, that roaring part, and I leave it there for a little while, there's loads of oxygen around here. There's loads of oxygen in the air. It's not limited by this collar or anything like that, and so that heat will be making the carbon react with the oxygen in the air. So when I lift this back up, what do you think you're going to see? Well, you're going to see the carbon has been oxidized and turned into carbon dioxide, and the carbon dioxide is gas. So that means the black substance should go, and there should be a little white dot there, or a lighter dot in the center. So that means you've oxidized that carbon completely. Now I want to compare the two again, but this time I want to do it with heat to show you the big difference. I've got a piece of paper, and don't do this in your laboratory. Your teacher will not appreciate you leaving burnt bits of paper everywhere. Okay, so don't do it. But if I take this and just put it through, you can see it's not burnt. Okay, it's not burnt. That's because this is producing much less heat. Don't get me wrong. If I put it in there for a long period of time, it would burn, okay? But let's put it in for the same amount of time, but with the complete combustion. And you can see straight away burns. And that's because this is producing, it's a lot more efficient, it's producing a lot more heat than this, okay? So this is bad for many reasons. One being, it doesn't produce as much heat. That's why if you burn coal and things like that, coal burns incompletely, and therefore you produce less heat. Also, it produces carbon. You might be able to see a slight bit of carbon coming off the flame here as well. But if you put that into an equation, the equation is propane plus oxygen goes to carbon plus water, and that's your incomplete combustion. You can see the carbon is not oxidised because of the limited amount of oxygen. And then we go for the carbon monoxide, so C3H8 plus O2 going to carbon monoxide plus water. You can see that the carbon now is partially oxidised with a little bit of oxygen. So you can see those three products. We've got carbon, carbon monoxide and carbon dioxide. Carbon dioxide is your complete combustion, carbon monoxide and carbon is your incomplete combustion. Now that we've gone over incomplete combustion and complete combustion, okay, it's time for us to go back to the studio where we'll continue talking about alkanes. Now that you've been to the laboratory and you've seen what combustion is like when you're using Bunsen burners and doing all the normal stuff hopefully you're doing at school, we're now going to talk about what it's going to be like to do in the exams. So, complete combustion. We recognise that blue flame. And then we have an equation here. So the important thing about the equation is, look, we are having 2 moles of oxygen here. We're creating the carbon dioxide and the water. So as you go to incomplete, which is the next part here, so incomplete combustion, less oxygen produces that orange flame and can produce carbon, carbon monoxide and water. So let's do 2 examples, one with carbon monoxide, and you can see here less oxygen, and one with just carbon. So you can see the amount of oxygen is going down, so it's being oxidised less, and as you can see there's less oxygens on the carbon, so CO2 going to CO, going to C. So we're getting less oxidation there. And that produces less energy as well. So if we're going here, balancing complete combustion reactions, so just complete combustion, I'm going to give you a task here and hopefully you will stop the video and do it. Here I want you to take methane through to pentane and balance the combustion reactions for complete combustion. Now, those equations, we can see the first one here and then the second one here, start to see a pattern. So this is what I'm doing this for. I want you to see the pattern. So if we've got ethane here, it's got 2 carbons and therefore 2 carbon dioxides. And the difference between here and here is an extra carbon dioxide. The difference between there and there is an extra water. The difference between here and here is 1.5 oxygens. And the difference between here and here is a CH2. So basically we can do an equation for every single difference. So let me put that through there. And you can see, let's look at this difference again. Again, the difference between here and here, CH2. Difference between here and here, 1.5 O2. Difference between here and here, 1 CO2 and 1 water. And that goes all the way through. Okay, so we can see the difference. That means the difference in energy produced between these, when you go on later to do energy calculations, should be a relatively similar difference in energy between each one. If you're determining it theoretically, obviously in the lab you lose energy when you do these, so it can be different. Okay, but we'll talk about that later. So if we then have a look at that and see what is the difference. So every time you go up by 1 carbon, you're taking a CH2, you're adding 1.5 O2, going to CO2 and H2O. Okay, so basically, just finish that off there. You got every single time you go from one to the other, you're breaking this amount of bonds and you're making that amount of bonds. So there should be similar energy difference between each equation. Our next reaction is going to be radical substitution. Substitution where you take an atom and replace it with another atom, and radicals unpaired electrons. If you're not sure about those, go back to our previous video on radicals where you can find out more about them. Now, the reaction is between any alkane you want, with a halogen, and in your course it will be chlorine or bromine. And this is by radical substitution using UV to start the reaction off. So that gets the reaction going. And it's a chain reaction. It just keeps going, keeps going, keeps going until the reactants have run out. That's because chlorine, the chlorine radical, is a catalyst, and we'll show you why that's a catalyst in the next slide. Now, the reaction we've chosen is methane plus chlorine goes to chloromethane plus hydrochloric acid. let's put that to the side and start looking about what you have to do for the exam. So what you have to do for the exam is draw a mechanism. Now, mechanism means two different things in organic. It means curly arrows and all this kind of thing. But with radical substitution, they want you to do these three steps: initiation, propagation, and termination. Initiation, creating the radicals; propagation, generating a radical from a radical; and then termination, putting two radicals together to give a non-radical, or just something that doesn't have a single unpaired electron. Now, the first bit is taking chlorine and having the UV. So this is really important. UV makes this happen, okay? And this turns the chlorine into two chlorine radicals. Now, if I go up here and I start putting this on here, what actually happens is the chlorine, which is bonded like that, okay? One of those electrons goes there, and another one of those electrons goes there. Now, that means this has a single electron, that has a single electron, and this creates this here. Now, this happens due to the fact that this has UV, so it's UV light making this, breaking this bond, okay? And also, as well as that, this is a type of fission which you'll need to say, which is homolytic fission, okay? So homolytic fission, okay? So, really, really important. Any question you got, homolytic fission, UV, and it does it because of these single arrows, because each one with a half head just moves one electron onto each chlorine. Now, you don't need to show this in the exam, but it's really good to recognise it and know why this happens. Otherwise, this doesn't make much sense. Now, you've created your radicals. Your radicals are really, really reactive, so they start reacting with the other materials that are in the reaction pot. So we've got methane going on there. So the next one is reacting the chlorine radical with methane. And you can see that it takes the H with it. So the H bonds with the Cl, that's why you get HCl, leaving behind the CH3 radical. And the same process happens, doesn't matter what starting material you have. In the first step, you will combine a H with the Cl radical to create HCl, or if it's bromo, you will create it, or bromine, you will create a HBr, and then you leave behind this radical, whatever's left behind. And in this case, if you take a hydrogen off the methane, you get CH3. The next stage is to take the CH3 radical, or whatever radical you produce, react it with another one of the halogens. In this case, it's chlorine, could be bromine. Now, if you then look at that, the next step is to split the chlorine up, and the chlorine reacts with the CH3 to create this chloromethane, and then the chlorine radical again. Now, this is a really, really important point. You've got chlorine here, which is used up, and chlorine here, which is regenerated. So used up, then regenerated. And we'll focus upon that again in our next example. But that means it's a catalyst, which means that this process keeps on going and going and going and going, because the chlorine goes right back to the start and then begins the whole process again until the methane runs out, which means it can be a huge explosion because it happens so quickly. So my A-level teacher, who I'd love to immortalise in this video, was Mrs. Roberts. And she told me about cows farting methane gas, which is a problem for global warming, by the way, if you know. And there's a train going past with chlorine on, and the train crashes, and the chlorine then spills out into the field. Huge explosion. That's because the sun is shining down and shining UV down on it, and the whole thing goes boom. Okay. And that's one of the only things I remember from my A-levels, those story. Now, next thing is to react the radicals to give a non-radical. This terminates it, finishes it. So you start it, you carry it on, you finish. Okay? And to do that, you just react two radicals together. So two of the radicals are the CH3 and the Cl, because there's Cl dot here, there's CH3 dot here. Just react those together, you get CH3Cl. Or you could react, what if there are two particles of CH3? They could react together. And then you get non-radicals, or ones that don't have a single unpaired electron. So if that's the case, it's the same process every time. So what we're going to do is move that to the side. Okay, so we move that to the side, and then from that point, we're going to do this exact same thing, but we're going to do it with ethane. So I want you to stop the video and do it with ethane instead. So ethane is going to be C2H6, and we're going to this time do it with bromine just for difference. So we've got bromine. We look up here, it's going to be C2H. We take one of the hydrogens off. See, the hydrogen is going from there to there. It's going from 4 to 3. So this time it's going from 6 to 5. Okay, and we bond it with the halogen, just like we've bonded it with the halogen up there. Okay, and this time instead of HCl, because it's Br, we have HBr. That's our overall equation. Then we do our initiation, which I'm going to do with a big I. We have our propagation, P, and then AD. So, initiation. Well, bromine, we take a halogen, we turn that into radicals. We need to get the radicals going. So that would be Br2 going to Br dot, and there's 2 of those. And to initiate it, we need UV. Now, as well as that, got to remember this is homolytic fission. We do every single mark on here. So this is mark worthy straight away. Right. We then do propagation. Now propagation is going to be, we use the Br dot, and then we add the Br dot to, from there, we're going to add the Br dot to the C2H6. So we add it to our original, and we're going to see the hydrogen react with the bromine, so we get HBr. Okay, and then that means I've lost that hydrogen, so I'm remaining C2H5 dot. So that's our first one. We then go to the next one. We say, right, this radical, because the radicals always react, dot, then with Br2. Okay. Now with that Br2, the Br reacts with this C2H5. Okay, and then it leaves me with a Br dot. So really, really important when we're looking at this. Here, if I highlight it, there's my Br. And there's my Br. Okay, so what I've done is I have used up, and then I have, from this point, regenerated. Okay, used up, then regenerated. Therefore, that is going to be a catalyst. Okay, so that's going to be a catalyst. So we've got a catalyst here. Really important, could be mark worthy again. And then we just do a termination step. So termination step can take anything in here and just join it up. So let's just take any radicals in here. Or let's take a Br dot C2H5 dot. And again, they don't worry if you don't put the dots down. Okay, they don't worry too much about that. And then that's C2H5 Br. You can combine C2H5 as well with C2H5, 2 radicals, which is C4H10. Now, we've got all our marks. We've got initiation, propagation, termination. We've gone through the entire thing with a different one. And remember, this is a radical chain reaction, which means that you could start this entire process again with C4H10, put C4H10 up there, and go through the entire process again. And you can make a mixture of products, and that is the problem with radical substitution. It doesn't stop. It goes in all different directions. You can make lots and lots and lots of different products, and we'll talk about that in more detail in a minute. But it also means you can put bromines anywhere along the chain. You could put multiple bromines on the chain. So really, it's really unpredictable. So you can't use it that often. It's just a big explosion. We're now going to try and put this in a bit more context. So let's imagine that you have this reaction, but you have this reaction in a flask, and we've got this all in a flask, and it's a liquid or a gas. It doesn't really matter. Now the fact is that this is a sealed system, and nothing's going to escape. So if we look at our equation over here, you can see if we've just taken some of these different reactants and products and just put them into the pot, and you can see them into the pot there. And want to give you an idea of how unpredictable this is and how you can maybe do some small amount of prediction, and then we'll go into an exam style question that uses this. So if you've got all of these in here, that means that they can react together. That means anything from any step can react together. So if that's the case, we can have more than one CH3. So see, I've put a CH3 there. There's billions of molecules in here. So, okay, so there's got to be more than one of these things. So I've got two. What's to stop those CH3s, like we've done in the termination step, combining together? And you can see they've combined together there to make ethane. Now, also, what's to stop the Cl dot now reacting? Because the Cl dot over here reacts with the methane, but what if the Cl dot reacted with the ethane once you've produced it? And that's the next part. So we create this HCl, and we've got CH3, CH2. That's just the same process. If you want to look at it, same process as that step one, but with ethane. Now, there's billions of these molecules in there again, so surely there would be more than one of these. So we've now got two. There's billions of them, so it's just a simple representation. And what's to stop these two combining together? Well, they would. It's just a termination step. So they combine together. Okay, and you'll get C4H10. My point is this, is that this will just keep going. So C4H10 might react with a CH3, with a Cl dot, and then that would create C4H9. That C4H9 could react with a CH3 dot, which means you can get any number of products. If you've got a starting material of only one carbon, that means you can get anything you want, any length. Okay, and I'm going to show you in the next slide a simple way to get a molecular mass from this and predict what the identity and what the molecular formula is of the compound once you've got a molecular mass. So here is our question about identifying that product. So this time you have the product of the reaction of chlorine with methane under UV. Okay, relative molecular mass of 78.5. Now we've got a little tip here. If you ever have a question that's like this, you've got to look at this 0.5. Okay, so you've got to look at that 0.5 and go, right, okay, what does that mean? Oh, chlorine. Well, what is the atomic mass of chlorine? So that's where our tip comes from. So the atomic mass of chlorine is 35.5. Well, that 0.5 must be from the chlorine, and it suggests that it's one chlorine because there's only 1.5. It could be three chlorines, but they'll never ask you anything that complicated because it's really hard to predict. So 0.5, one chlorine. Now, if that's the case, there's a simple way of doing it. So what you do is you take the 78.5, okay, and you've got your 78.5, and you take away from 78.5, 35.5. Okay, so 35.5 is your chlorine. So that means you've got, from that, 43. So 43. Now, you might ask, why would you do that? Well, everything is based upon alkanes. So we're basing this on this alkane. So you've got this methane here. So it's based on an alkane, and it'll become an alkyl chain of some sort. And you know it's only got one chlorine on it. Well, if that is the case, if you look at alkyl chains, as part of their homologous series, are made up of CH2s. So a change is CH2, 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 and then a CH3 at the end. So roughly speaking, what we can do is we can say, well, CH2 is, the mass of CH2 is 12 plus the 2, which is 14. So that's 14. Let's put the units in there just to be clear. So that's 14. So what we can take is then say 43 divided by 14 would roughly tell me how many CH2s are there. Now that equals 3.07, and that's a number like that. Okay? Now I don't care that that's not exact, because I know there's in a alkane, there's CH2, 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 but at the end is a CH3, so it's not going to be perfect, it's going to be a roundabout. Now if that's the case, that means you will equal 3 carbons in the chain, okay, and most likely 3 CH2s. So I can base everything off that, and I can say, right, okay, if that's 3 carbons, I can C3H, and I know I've got one Cl. So I can say, well, how does that work with an alkane, haloalkane? Okay, alkanes are CnH2n. Okay, and if it's a haloalkane, it will be +1, and then whatever the haloalkane is, in this case it's Cl. Okay, so 2n plus 1. So if we look here, 2n plus 1 is 7. Then all we have to do is do a really quick check, and honestly this happens really, really quickly. If you're used to doing this, it's a really quick process. Okay, if you look at this and just add it all up, so that basically will mean 3 times 12, okay, plus, well, we've got 7 hydrogens, so that's 7, and then plus 35.5, which I am really hoping that you've put it in your calculator and you'll see that that equals 78.5. And if it equals 78.5, that means your product is going to be C3H7Cl. And this question will only ever ask you the molecular formula, so don't worry about any other detail than that. So now we're going to go through a very similar example where you're looking for that molecular formula and you're looking for the product, this time with bromine. Okay, so really important. And we've got UV again, homolytic fission, 122.9. So the tip is going to be here, you've got the atomic mass of bromine, which is 79.9. And this time, if it's 79.9, you're looking for the ending to be 0.9. But they can make this a bit more complicated because it can be 0.8, because 0.9 times 2 is 1.8. So it will end up being 0.8. Remember, carbon and hydrogen with these things are all kind of whole numbers. So they're all whole numbers. So this will indicate that you've got 1 bromine or 2. Now, hopefully you can do this yourself. So stop the video, do it. Okay. Now, what we have here is we have 122.9. Okay, we're going to take away as we did before. But this time it's bromine, so it's 79.9. Okay, and that will equal, which is handy, 43. We know that that is the carbon chain remaining. The carbon chain is made up of CH2s. A CH2's mass is 14. So it's 43 divided by 14. 43 divided by 14, again, it's the same as the last question, 3.07. Okay, and therefore that equals 3 carbons, we think. Which means then we can go, right, okay, let's look at this again. We know that this is CnH2n plus 1, and then this time with the Br, because we know it's 1 because it's 0.9, so it's 1 Br, so it's that. Therefore, it'll be C3H7Br. So that should be our molecular formula. And all we have to do is a really quick check. And if you do that, 3 times the 12 again, plus 7, plus 79.9 equals 122.9. So we're now on to our final part of this reactions of alkanes, which is limitations. So limitations is something that normally a 1-mark question or something like that. And there's 2 limitations, which is further substitution or reactions at different positions in a carbon chain. Now, what does that mean? So what that means is, if you remember from earlier, we can make anything from methane. So we can make C2H6, we can make C4H10, which we made in this pot here. Now, if I look at C4H10 and I go, right, okay, there's C4H10. Okay, so we've got C4H10. And then from CA4H10, further substitution means, for example, we could put a chlorine on here. Okay, so there's your chlorine on here. But that molecule might go back into this, into this pot. It might react with chlorine radical again, and then it might further substitute, which means you might get more than one. So you might get one here as well. Okay? Now that could carry on. You could get more than that. You could get another one here, another one there. That's further substitution. So limitations are you don't know what you're going to make. Okay, because this chain reaction keeps on going and going and going. Reaction at different positions on the carbon chain. Let's take our carbon chain we've got here again, C4H10. So I could make one of my molecules. Okay, let's draw 2. Okay. And on there, I could have one where the chlorine was at position, let's put it at number 1 here. Okay, and there's your chlorine. Okay, and that's at position number 1. But we could have another one where it reacted at position number 2. Okay, so really important. Okay, that you can do it at different positions, so number 2 and number 1, or you can get multiple substitutions or further substitutions, which means the limitation is you don't know what you're going to make. So it's a problematic reaction and one which you can't really do with any certainty as to what you are going to make.